back, just raise your hand and say, because I'll tend to soften up. But I'll try to do my best to get everyone to hear. So I did take the class from my dad. He was tough. And but I think I survived okay. And so I really enjoyed my time at BYU. I feel like I was treated quite well here. And you'll see why when I get to the end of my talk. And I've enjoyed my career and the things that I've done. And I think I have a few things that, one of the things I've realized when I look back upon myself, when I was, and this talk is really geared at freshmen and sophomores and maybe juniors, it's really geared to this level. When I was your age, I really didn't know much about what was happening in the world and where the research areas were and what the fields were. So part of my reason for being here is I want to at least give you a heads up that I didn't have. And I think the math department is doing a really great job in trying to give you more heads up about what's out there and what your potential is. So that's one of the major goals. And hopefully I'll at least introduce a little bit of math to some of you that you haven't seen before, so you will not be surprised when it hits you when you hit graduate school or your job. So that's another goal. Okay, so this is what's going to happen. I'm going to talk to you about Sandia, what it is. So I bet, who knows what Sandia National Laboratories is? That's about what I thought. 10%. Okay, I'm going to talk about what I do, and along the way I'm going to throw in little math singers. I'm going to name drop math topics, okay? Just to say that, look, this part of math could apply in this area. So I'm going to do a little name dropping. And at the end, I'm going to talk a little bit about how I got to where I am and what you should do if you think the kind of stuff I do looks quite interesting to you. What might be some good ideas? So that's the idea for this one. Okay, so what's Sandia? Well, Sandia is what's called a federally funded research and development center. So I'm not a federal employee. I'm an employee of Sandia Corporation, which is managed for the Department of Energy. The laboratory is managed for the Department of Energy by Sandia Corporation, which is a Lockheed Martin company. So it's a government-owned facility and contractor operated. So DOE has, Department of Energy has a lot to say about what happened, but it really is a separate company run under contract. Okay. All right, so where is Sandia? Sandia is in Albuquerque. That's where most of the people are. The next big chunk of people are in Livermore, California. Sandia has a site just south of Lawrence Livermore National Laboratory. They're right next to each other. So there's two laboratories sitting right next to each other. And we have much smaller locations in Texas, Carlsbad, New Mexico, Nevada, and Hawaii. So those are the two big spots. I live in Albuquerque. Okay, so what has Sandia Corporation been doing? Well, it started in 1950 in the world of nuclear weapons, just coming in, and it began growing through the 1960s. It started to become a multi-program laboratory in the 1970s with the energy crisis in that time period. We got the Cold War coming in the 1980s, the same year was involved with trade issues at that point. And as time goes on, we have stockpile stewardship issues. When I say stockpile, that means nuclear weapons stockpile. So that's what that's one of the main major things. Right now, it is there's life extension programs for nuclear weapons rolling forth, and a number. If you read the news at all, you know that there's a large number of national security challenges that the United States faces. And Sandia is involved in almost everything, I would say, in some way or another. Okay, so I'm going to go through a few slides, give you a big high-level overview. So we have a big pulse power facility at Sandia called the Z machine. This picture's come up a lot. Actually has a lot to do with the modeling of that, the relationship there. A lot of system engineering, non-nuclear components, and production as well. Nuclear weapons area. This all happens at Sandia. There's a large amount of work in defense systems, DoD, all sorts of defense systems, in synthetic aperture radar, missile defense, sensors, a lot of stuff. Also these days, there's a lot of security issues that have to do with energy and infrastructure and the security of national infrastructure, these possible threats. Climate is changing, and that has security implications as well. So you have bioenergy. Okay, also homeland defense, lots of different programs and applications in homeland defense and asset protection. Okay. Where I work is more in the science foundations area. And there's science foundations that support all the rest of that, include computing and information sciences, exascale computing, material sciences, engineering sciences, modeling, and what we're talking about does fall into that a bit, also over in the energy density science area. So there's a lot of science involved in various aspects of national security and other work that we do. We also do work for others, meaning that a company can come to Sandia and say we want to do a collaborative research and development, and they can pay Sandia. So anyway, so how big is this endeavor at Sandia? Well, the gross payroll is just under $1 billion a year. That's how big it is. And we have about 10,000 employees, slightly over 9,000, and people working at the lab in one form or another as contractors, close to 12,000. So there's a lot going on. Okay, now that's sort of what Sandia is. It's one of the major DOE laboratories. So there's a number of national laboratories that are run by the Department of Energy, and Sandia is one of those major laboratories. Okay, so if you look at the research and development staff at Sandia, this is the breakdown. 50% in computing, mechanical engineering, electrical engineering, Now notice mathematics is a very tiny slice. Okay. And there's physics and chemistry. Now right here is when I was hired in 1983, I was brought in as a mathematician. So that was my HR title, right? Because I graduated in applied mathematics. But I was brought in as a mathematician in this very small slice. But what I really do actually is in all these blue dots. If you look at my day-to-day job, from the time I got to work, this is the kind of stuff I really started to get involved in. So you can take from that my degree was in applied math, and the reason that I see that it was allowed to kind of move this way, in fact, it's critical, I think, to be able to do more things than just one small little segment. It's really important. So I wanted to show this just to point out that I view math more as foundational technology that allows you to do a lot of things, get into a lot of areas. And in fact, in my applied world, you pretty much get some problems. So that has implications. Okay, so I'm going to show this slide a couple of times. So the work I do is actually over here. So this shows what's called a a multi-scale modeling interface. So we talked about the Z machine, and here's the Z machine over here. This is about as big as a warehouse. The load where everything really happens is about this big, like this, something like that. So what you have is a bunch of capacitors. You dump them into pulse forming, you dump the energy into the pulse forming lines, and eventually all that energy gets dropped into a very small area. And that's where they do experiments. So in order to model scenarios like this, what you'd like to do is call this the macro scale, the component scale. This is sort of the scale we live at. You'd like to be able to model that world. But to feed up into that world, we actually have to know what the material properties are, how everything interacts, and what the equations are. And in principle, you could start out with very fundamental equations. The Dirac and Schrödinger equations of quantum physics. You've got those equations, you can really know everything about the way the world works. People are pretty convinced that these are really good descriptions. The problem is that they work at the atomic scale. And you can't solve these equations at this scale. You don't have to solve them at all. So what you have to do is build bridges that move you from this sort of description to a higher description. This is density functional theory. For density functional theory work, you have to have what's called exchange correlation functions, which are representatives of what really is supposed to go on. You get hooked up with molecular dynamics, and you can start to provide data that can go into what I'm going to explain in the next slide or two, are closure properties. And those properties then affect the modeling that you do that then describes this macro scale. So this kind of idea that at some level we ought to be able to predict anything that's happening at the macro scale if we know enough about the micro scale is part of what computational science and engineering, that's sort of the grand vision of what we'd like to do. Nowhere near done, but that's what we'd like to do. Okay, so what do I do? So this is my code that I worked on with my team. It's called the Ledger. It does what's called magnetohydrodynamics model. And this is a configuration of what's called a strip line geometry in the initial code. And to model this, you need what resistive MHD, you need accurate conductivity, you need a lot of stuff. And you need closure properties to describe the states of the matter very well. And if you do have this all really put together right, then you can, let's see if I can make this work. Yeah, so you can see this magnetic field right here is blowing this apart. Let's see if I can make that work. Okay, see this line right here? This thing is coming in, it's going to impact right there. So all that big technology, that whole room of equipment, is all designed to try to do experiments at this kind of a scale. And in order to design the experiments to make it all work right, you have to have a good modeling capability. If you don't have a good modeling capability, you cannot really do it right. So in the last 10 years, we did a fairly, been great success in getting enough of these properties right and modeling equations right so that they can pre-design the experiments to try to get into different states of matter and examine those states. So you really need good computation in order to even design the experiments that you do. Okay, so what do the equations look like? Now, so these are actually very common equations: conservation of mass, momentum, energy. This is magnetic flux. All these terms mean something. This is the curl operator. If you've been through this third semester of calculus, right? You probably know what that operator is, and the divergence operator. This right here, this dot, doesn't mean something very specific. That's the total derivative. And this is what's called the conservation mass equation. If you look at it, so you can also write this in integral form. And what this equation basically says is if I have a region of space that's moving with what the material particles are moving together, that the total mass doesn't change. That's conservation of mass. But when you work it through, you actually get an equation, partial differential equation that looks like this. I'll tell you what this dot means. So you have a lot of different operators. So the key point about this slide is these are the equations that tend to really describe the kind of work that the predictions and analysis that I was talking about. They are wonderful equations. They are wonderful, except for the fact that you have to close them. You have to have relationships that make all these terms in the equation depend on terms, basically the dependent variables that are in the equation. So the stress has to be a function of density and energy. And the conductivity is a function of density, temperature, which you write in the equation of state, and the heat flux. So all these kind of things come into the equations. And the key point that I want you to remember is unless you have those relations, those Fourier relations right, you're not going to be predictive in any sense. So the big deal is, given a good set of equations, how do you close them and how do you have equations that work? Okay. We'll talk a bit more about that. Okay. All right. You've seen this equation before. Right. You. Okay, can we turn on the lights? Okay, so this is one of those things that you might not see in your undergraduate world, but I would really like you to see it today, so that when you get to graduate school, you've already seen it. Okay, so this equation is the most fundamental nonlinear hyperbolic equation that's out there. The hyperbolic equation has to do with waves. So what we're going to do is we're actually going to solve that. So u is a function of x and t. So u is whatever variable is the density. Let's call it velocity. Okay. So that's the equation. What we're going to do is the way the mathematicians and the physicists always talk about this is you write x in this axis, t on this axis. And so you have an initial condition at time t equals 0. And then you want to find the solution as time progresses in space. Okay. So how do you do this? Well, one way to do this is you write the total derivative. So that's that u dot, and here's another form, du by dt. And you'll also see it like this, du by dt. Okay. Total derivative is equal to partial u with respect to t. If we think of this, now we're going to put a t in there. So we're going to take the derivative with respect to time, and then this will be dx by dt times partial u with respect to x. So then what you can do is you can say, okay, well that's nice. U dot equals 0 as long as dx dt equals u, which is that equation. Okay. So we can start on a point here on this line. And and here, this is called this the initial state C. So here's C, and here's U. So now, but wait, U is constant. So we can integrate this. So X is U, and let's just tag it by C. So when t is equal to 0, X is going to be equal to C. So for any c that c is constant, and we have a straight line, so let's draw it. So there's a solution, whatever u is, along something called a characteristic, that solution is constant. Okay, now let's do something else. I'm going to rewrite this. So that's the equation of the characteristic. So we can think of t. So the slope of this line is 1 over u. Okay, now the last thing to observe is what if the initial profile looks something like this? So, and this is u, and this is c. Well, if u is small, then this would be big, the slope will be big. So let's do this. It's going to look something like that. And then as it gets to the top, it's going to look something like this, and it goes down. So let's keep going like this. We're going to come back this way. As it gets further and further down, it's going to look like that. Okay, so now we have solved this nonlinear equation completely. What's wrong with this picture? Anything wrong with this picture? Anything? What bothers you?
The lines cross.
The lines cross. So what does that mean?
The solution's not uniquely determined.
So there's actually there's multiple solutions here, right? Okay, so that's a modeling problem. That doesn't seem right. So something's broken down. So actually what we do, so there's this region where things cross, where the characteristics cross. Okay. So what's a shock? A shock, you can fit a shock in the middle of it, so they don't cross. So a shock is where those characteristics cross, and you have to do something else. Okay, that's the simple story. That's what a shock is. And what really happens physically is something here. We go to this parabolic equation. So many of you may have seen the heat equation. That's what this equation. This term, this double derivative term, means things want to smooth out. So if you add to the Berger's equation this double derivative term, what happens is the characteristics tend to cross, and then this double derivative in x term smooths it out, so you don't get a multi-value solution. But that's basic nonlinear hyperbolic equations. You know where you're going from here. So that's where it starts. Okay, I gotta keep going. I gotta find where I did this. Okay, so now if we go back to the MHD equation, now it's really complicated. So you get multiple characteristics going in two directions, and this is just in a one-dimensional case. And you have fast mode, alpine mode, slow mode, and if you just have pure gas dynamics, these normal shocks, you tend to only have 3 eigenvalues or 2 modes. You have contact states, forward and backward propagating shocks. Okay, so things can get really complicated, but that's the world of nonlinear hyperbolic equations. And a lot of modeling that's really important has to do with that area of math. Okay, so so what do we do if we want to model this on a computer? Well, here's a solution, and I've shown where the magnetic field is, and there's an explosion happening here. And you're seeing some magnitude of magnetic field, and this is the current density normal to the plane. So what you do on a computer, you have hyperbolic equations. You divide in a parallel computer, you divide the system up into each little part of the domain to some other part of some part of the parallel computer, and you go. Now what happens when you hit a boundary? You've got to do a communication. I was going to do an activity, but I don't think we're not quite dense enough to make it work right. But what I was going to do is start here, raise your hand. Well, actually, let's try it. You raise your hand, and if you're next to him in some sense, you raise your hand too. Okay? Okay, go. Okay, great. So we just saw a hyperbolic wave. Very good. Okay, now, if we were on a parallel computer, I would not allow you to make that connection unless you're closer, right? So let's do it one more time. And if you have this big space, you guys have to get up and get closer before you raise your hand. So let's do that one more time. Go. Wow. You really have a heterogeneous media here. Okay, what did we observe right here at between the different processors? What did we see happen? Whether as a media, somebody had to stand up and walk, right? Okay, so that's computer science coming in. There's some latency. If you're going to communicate between one processor and another, there's some latency involved. You got to deal with it. Okay, so there's my computer science. That's an example of the kind of stuff you have to think about when you're solving equations like this. Okay, so that's my demonstration of local communication. So when we write algorithms on the computer, pretty much we want scalable algorithms. What this means is if there's order n number of people, right, in the room that have got to propagate information, in order to go forward one step, we only want to do order n work. So everyone was doing order n work from left to right before they raised their hand. Maybe kind of every half a second, right? That would happen. So that's good. Now if you get other kinds of algorithms that are trying to do that have longer reach, then it gets harder. Okay. And this statement here has to do with, so right now you live in a wonderful time that parallel computing is going through a fairly major change because we've kind of hit a plateau. We can't really make things that much faster. So that all they can do is sort of give you more processors. So now we're going into not only, say, message passing that we kind of demonstrated here, but we have to do also local vector parallelism is much more important and more important. By the time you get to graduate school or even now, the whole idea of building algorithms is going to look at multi-level memory hierarchies and as well as communication. So it's getting a lot more difficult actually to really push forward in the computer science area. Comment on speaking computer languages. In my world, it's really important to actually be a pretty good software engineer, meaning that you need to know a lot of stuff, Fortran, C++, Python, whatever it takes to kind of work in a group and get all this infrastructure to make this technology work. So there really isn't a lot of room for being a language bigger or something like that. You just have to be responsible. Okay, here's some math. I'm going to drop some math here. So this is what's called the Theorem complex. So it turns out in MHD, it's really nice to work with finite elements or discrete elements that represent differential equations that have nice properties that send you from one space to another space and a null space, which is I can't go into it. There's stuff that happens between these different types of spaces that are really important to make all this on a computer, make the equations that we wrote down, which we believe matches the physics system to make it work. So it turns out that using this kind of math is really important to make this stuff work. So what is the math? I'm going to drop some names, function spaces. Details of the null space can be very important. So the point is, the stuff that people that work in function spaces and math, at the end of the day, actually turns out to be very important for people that do real computing like me. Okay. So here's an example of the divergence theorem. So if we have a code that is an AL code, arbitrary Lagrangian Euler, and we move forward, and we have to remap. And to do that with magnetic fields, which has to preserve this the B property, divergence B equals 0 property, we have to actually use this constrained transport idea. And what you do is you have to compute on the edges some fluxes through faces in order to compute the final answer on the new face. And it turns out that when you have to compute on edges, in order to when you take a discrete curl, in essence, of this mesh, that you get all the nice properties of discrete divergence-free properties ending up at the end of the day. So here's some more math coming in a finite algorithm to solve physical equations. Okay, here's some more math that's come up in my world. So when we build codes, we have we tend to build codes, big codes, with thousands, millions of lines of software. Okay. the end of the day, you want to know whether it's worth anything, and we can build general codes. So one of the things you can do is you can do some math of complex variables and special functions, acceleration techniques. And this work then feeds into a nice exact solution which we can use to test with general code. This is work, actually Brad is here, he helped me last summer trying to pull this together so that the other researchers on the team can use this as a benchmark problem. So we're bringing this word verification in. Verification is your numerical scheme on your computer giving you the answer that you thought it should when you wrote your equation. That's what verification means. So there's a number of different frames of reference and angles we want to test out and check. So this is an example of a student project, and very important because we're trying to verify that our code is robust and works properly. That's an example. Okay, so that's what verification is. These are terms that are very important in my community because you want to keep your logic straight about what you did. Verification means you write down your equations and you prove that your computer solution does exactly that. That's the idea. Validation is a separate question, and these are very specific terms and they're used in the community. Validation means, am I solving the right equations? Does equations mean anything? Okay, and it turns out equations are not just given to you and they're the ones you have to use. You have to actually work at that and decide what the best equations are. And the equations are good for the purposes that you care about. And so here's an example. We took the MHD equations in this particular form, and we wanted to simplify it in some way in this limit. This non-dimensional limit is the conductivity, this is the length scale, and the time scale, this is the permeability. In this limit, then we can simplify and show that these equations likely are very well approximated by these equations in this limit. And if this is a limit you're living in, it's a lot simpler, maybe a lot better. So here's some math: dimensional analysis, asymptotic analysis. Those are kind of things that come up in my world. Okay, next subject. Uncertainties. Now, nuclear weapons. No one ever wants to use a nuclear weapon, right? And we certainly don't want them to go off when we don't want them to go off. We want them to be very, very safe. And you want them to be credible at the same time. And we don't even do testing anymore. It's been over 15 years or something that we've been doing testing in the United States, and there's no plan in the future to do it. So a big area is what we call uncertainty quantification. You have a set of modeling equations, and in principle you can solve them on a computer, but in reality the equations and the inputs are uncertain. You don't really know them. You only know them at some level. Well, at what level? How good? So now you have to bring in all sorts of named math, probability theory, Bayesian analysis, markup, chain Monte Carlo, random field variables. So in effect, now we're saying we've got one more dimension, a random dimension to our solution. And maybe what we really want is some quantity of interest at the end of the day that tells us we want a distribution. What's the probability that this was some value? So if you want to go to Sandia.gov, Sandia has a freely distributed tool that does a lot of this kind of work, including optimization and things like that. So this is a black box tool. So here's an idea in the project that I'm working on now. We're trying to build an equation of state, but we also want to try to build it uncertainties and propagate them all the way through here. How can we propagate uncertainty from, say, this scale up to this scale? Right? So what we really want at the end of the day is essentially, in the engineering world, something equivalent to a 50% chance of rain. What does that mean? Okay. Now, what's 50% chance that the component is going to fail? Now, those are the kind of words that now people are starting to talk about. So now you've all of a sudden, to your PDEs and all this, you've now added a stochastic dimension of probability theory. And that's the way you talk about the world. So that's kind of the way we like to go here. So all we're trying to do right now is trying to find a way to represent the equation of state surface that feeds into the continuum scale model in a way that has some random character. Okay? So now the equation of state has some random variables associated with it. We want a mesh that represents it. Turns out we want a series of meshes of different instances of equations of state. They have to be smoothly varying functions or varying maps of each other. So here's what's called a Laplace Beltrami equation. And that helps us do that. And so in this whole project, there's some more math, differential geometry, calculus of variation, finite elements, singular value decomposition for the dimension reduction. Those are the kind of math things that we talk about. There's a student project. You don't always know what you've done at your initial condition, where you'd like to say, what's the consequences of randomness in my initial condition? Different ways to represent that. And this student, Emily's project, this last summer, we actually had a bug. We could never figure it out for a long time. One of our principles is serial parallel runs ought to get the same answer. And we weren't getting that, so there was some sort of bug. Actually, it turned out to be related to too much symmetry in our problem and then getting invariance, which basically in the decomposition of the variance. So now your linear algebra is coming in. So more examples. Okay, so summary. I really think that applied math is foundational to just about everything that we do. And that's really important. And in fact, there's a good question, so I'd answer it now, but you might want to think, can you really, every significant difficult problem I can think of that's international or national world today typically has a very important mathematical base modeling component that could really help. I think honesty is a big deal. You have to be able to deal with the fact that you don't know everything and what you're confident. You have to be able to describe that in some way, and probability seems to be the way to do that. Multi-scale modeling thing is really important. And I really believe that any competitive enterprise in the 21st century, to stay competitive, will have to get into modeling, probably multi-scale modeling, in order to stay ahead. Do that. Okay, so I think we're going to make it. So how did I get to where I am? So I started UIU with computational emphasis in the math department. I built a microprocessor and I hooked it up around the burned out some circuits. And I decided I would better virtualize. So I did on a computer pretty much ever since. Physics, statistics, a little bit of chemistry. I didn't learn enough chemistry to realize how deep and really interesting quantum chemistry and foundational equations of matter really are. There's a lot of math there. There's really interesting math at the foundations of material science. And that's a big deal for the future. So a little sad, but that was, it's only been in the last 10, 20 years from that really kicking off. Didn't get everything, that's the way life was. I had a professor, Richard Nixon, he's not passed away. But I took numerical analysis from him and he gave me a job. And I worked at IRE Research Institute. I don't know if that's still in program or not. But we did Minuteman missile simulations. I did numerical ordinary differential equations and rigid body mechanics. And I did my honors project there as well. And that essentially was from this work. And I also worked for Professor Beal. I really think that internship, particularly this one, the fact that I was involved in that allowed me to get into graduate school, which was Caltech. I went to Caltech. I sort of learned, first time I learned about continuum mechanics, which is theoretical fluid mechanics. really good grounding in complex analysis, asymptotic analysis, all these different areas. I worked in fluid mechanics, theoretical fluid mechanics and fluid stuff. Probably could have used a good theoretical continuum mechanics course. I'm sure that seems to cut some of it to be able. But that would have been really useful. So then I came and went to the shock physics modern world. Okay, so you've seen a little bit of my life. If you think you like it or it might be interesting, what would I suggest? Well, first I'd suggest is you got to go for it. You got to know a lot of stuff. So don't sell yourself short. Try to get as much interesting math, physics, computer science, material science, physics, chemistry. Get as much as you can. You can't get everything, but knowing a lot is going to be important. As far as basically, you need to be able to speak computer languages that live in the world of simulation. And these are different editors, Linux, C++, Fortran, Python, Fischer, math equations, MATLAB is probably listed in one other thing you can do. The basic language and mechanics of doing research and working in this field is really important, and you can do that right now. You don't have to wait. Just get going. Work group skills. I don't know if in the classes that you take in mathematics right now, whether you have to do group projects and use version control systems to build software together. If you did, I would think that would be a really good thing on the resume. Because I depend on all of our team of 15, 20 people working independently and together, checking in code, doing tests, and moving forward right now, all the time. And we have to be able to work in this collaborative environment and make that happen. Okay, so I think that's important for an education program. I really think if you get an internship and you work in a real life world, your life will be changed. And if you can do it now, that'll open doors for the future. My opinion is if you can get a good job that gets you deep into research or R&D of some sort, and you do a good job, most likely they'll want you for that. And maybe like the telecommunicate. And the other thing is you need to know a lot of stuff, and you probably can't get it all from undergraduate school. If you really, really want to get into deep, exciting research and the stuff I've been talking about, you're going to have to go to graduate school somewhere. That's my opinion. There's really a lot of exciting stuff happening. Okay, so how do you get an internship? Well, it really helps if you do a good job and your professors can help you out. Get some useful basic skills that I talked about. Just forget about thinking that you're going to know everything. You just got to keep asking questions and see what you can learn. The other point I think is everyone has a lot of adults in your life. You probably never asked them what they really do. And some of them are really good technical people, but they're not going to tell you unless you ask them what they really do or what those opportunities are. So you really need to expand your network of contacts. And if you do get some contacts, follow up, be appreciative, personal. People are willing to help you if you are asking and willing to do it. It's all about interpersonal relationships in a lot of ways. There's science, but there's also a big component of working in groups, working with people, and being able to talk to people. Okay, so now suppose you really wanted to get an internship at Sandia. Sandia has a huge internship program. I don't know how many. Brad, do you remember how many? 500,000 interns. Several hundred at least. So it's big. It's only limited by the number of projects that are willing to bring on an intern. Okay. And the number of people that can get with that. So the way it works at Sandia is you submit your resume online, and then you have to watch and you have to look and say, well, this job came up and that job came up, and then you submit a resume. That might work, or it might not. It depends on if that person is trying to really, how well that's going to work for you. You will significantly improve your chances if you do your networking homework ahead of time. You really you got to know people. You got to find ways to get to know people, and somehow you got to do that. You go to csr.sandia.gov. That's the area I work in. We hire a number of summer students. We have a summer student series that the students have to go to. They learn a lot. They hear a lot of interesting fields, activities that are going on, and that works that way. So that's my advice as far as internship. It's really important for your future, and but it's not just on your resume. It's how much you work with people. It's going to make a difference in where you want to be. So that's it. Thank you.